or final exam is Saturday next week. I will most likely be in the air going from Vancouver to Toronto at that point, or maybe we'll be driving because we're living out of Toronto. We're driving from Toronto to here. You know, there's a part of me that wants to start swearing and yelling and giving the finger to the border guard, so he turns away the entire van. It'd make my life so much easier right now. So if you see like an international incident and you're like, hey, that's my physics professor. You know, I took one for the team, so I wouldn't have to go, and so I could be here for your fun and help you out here. But I suspect you're going to let us go across the border. So let's go through. There'll be somebody here for doing it. The actual format is going to have two parts. Part one, part two, kind of clever. Okay. This is going to be new stuff. So what's the new stuff contain? We're going to start with the inductors up until the end of the class. This will start with inductors. It should be. This is going to be the material from the first three exams. Now, since we just had the third exam, what I will do, and to encourage you to look over this and get it done well, I will basically, for part three stuff, I will take either exactly from test three or slight variations from test three and put them directly on. Okay? And so that'll encourage you to kind of look over stuff to make sure you really kind of have it cemented. Okay? So what you might want to do very well is look over, because I think the part that most people had the problems on were the first three, the conceptual part, and then up to questions three. I think that's where actually most people struggle with that stuff there. So I would probably look over that because you might get just either the exact same thing or slight variations on that. That's what my cats have told me this morning when they were grading. Okay, that makes sense. Who will be proctoring the exam? I honestly do not know. Maybe one of our physics majors. I will be taking my smartphone with me. And I might be taking my iPad too. I have no idea whether I'm going to have access to any internet stuff. If I do, I will respond. But if I don't, you know, I don't know if the time difference is between the West Coast, well, Vancouver and here. It's probably what 3 or 4 hours difference would be my guess. And I don't really have a good idea about the agenda for the meetings and everything else. So don't expect a speedy response. But if you have like a technical thing, try taking a picture of what you have and sending that to me. And I don't know, again, I honestly have no idea whether I can respond or not. So if I can, I will try to respond, but don't count on it. But certainly you're welcome to try. Question, and then again, I'll tell my colleagues that there might be 8 students from 126 walking around the hallways looking for someone to help them. And I'll let them know, and I'm certain they'll be more than happy to give you a hand on things. Okay, questions? Okay, so we're still doing AC circuits. And we're looking at, we have this circuit here, like this. That. We have an open switch here. And this had some qubits. And at t equals 0, we threw the switch. We close the switch. Okay, what we want to do is find Q as a function of time. Find Q as a function of time. And so what we started off with is this. So we're going to have this circuit here like this. If I had this circuit here, I would say that this voltage here, V, equals this voltage here, plus this voltage here, because they're in series. And in this case over here, you can see there is no battery. There's no battery here. So I can kill this here, and so this gives me VC equals minus VL. And what did we say VC is? Q over C. Minus, and what is the voltage across an inductor always? L d I dt. Oh, before I forget, Michael, you handed in corrections for the exam, right? Did you hand in the original exam? No. Okay, well, could you hand it, because I need that to do to figure out how much day it had. Because I was looking over something and there was a test handed in. I thought I recognized your handwriting. I wasn't certain, but then there was no other counterpart. So just hand that in before you lose something like that. Okay, now what do I do with my buddy I? I is always dq dt. That gives me this. Okay, so what we want to do is actually solve that equation. And it turns out that's one of these equations that in physics, when you see it, you rejoice because that turns out to be your bestest friend. I want to convince you that this is actually the equation of a spring. And when you take the optics course, because I know a lot of you are taking the optics course, I'll show you explicitly how to solve it. Here we're going to kind of cheat to figure it out. In optics, I'll show you exactly how to solve it. It's one of these that it turns out to be really, really easy to solve. There's a cute little way you approach them, and you can actually, you develop a sledgehammer that there's a huge class of differential equations. You can just knock out the solutions very, very easily. And this is one of them. But I'll see how we can do this. So this equation here, this equation for the LC circuit is just the equation for a mass on a spring. Okay, and let me convince you of that. So if you look at this, here's a wall and here's a spring. Here's a mass here M. Let's say this is frictionless. Like that. So this is going to be my x equals 0. So if I stretch this out to, let's say here, where this is x, what are all the forces acting on my little friend there? Gravity in the spring. And so you have gravity going down. You also have the normal, but then you have the force of the spring, just going this way. So you know your F naught in the x direction is max. And from that picture, what are all the forces in the x direction? The force of the string. And from first semester, what is the force of the string given by? Kx. That's going to the left, so it's going to be minus kx. So this would be minus kx, like this. And we know that ax is really dvx dt. Hey, does the x velocity have another name? dx dt. So I can rewrite this as m second derivative with respect to x dt here like this. So to put this all together, what do we have? We're going to compare them. So this one we have minus kx here. But let's compare. Do this right here. 2, and I'll take over the minus sign here to make it a little more obvious. You see there's a one-to-one correspondence. Basically, the x goes to q, right? Instead of having an x here, we have a q here. Instead of having an x here, we have a q here. What does k go to? 1 over c. 1 over c. What about mass? L. That goes to L. So for any of you who are taking my classical mechanics course in the fall, It turns out when we look at springs, I'm gonna then do a little thing saying, hey, look at this electrical circuit. And you're gonna see actually that it's gonna have the exact same mathematical structure as the spring. So you're gonna have, there's a whole bunch of electrical circuits that we can actually solve exactly because we know exactly how it has to behave, which is kind of neat. Okay, now what's the advantage of this? You know what the solution is. If I were to say, tell me what, if I were to say solve X as a function of time, you know what the answer is, even though you don't know how to solve the equation. If I have a spring, and we'll move out the mass here and I let go, how's this mass gonna move? If it's connected to a spring. Hey, does this have a name? This is a sine or a cosine. So actually, I can already guess the answer here. It's going to be a sine or a cosine. So we'll do that. Let's figure out what we're going to do, and then we can then apply it to here. And so we know that a spring has to have x, the function of time, being either some amplitude, say some amplitude, okay, times a sine or cosine. Okay, as a function of t. So what we're going to do, we're going to guess the form. So we guess the form of x as, so I can call my amplitude here A. I could use a sine or I could use a cosine. It doesn't matter which. I'm going to use a cosine. Why would I use a cosine if I have my spring here like this? Let's figure out. So here's my spring. I stretch it out some distance like this, but then I let go. Cosine starts at 1 as I do it. The sine would start at 0. So if I had let's say I had a mass here, and let's say here's a spring and it was unstretched, and then I come along and then kick it or give it a push, then I'd use a sine. Okay, so I can use a cosine, but I could just as well use a sine there. Then I'm going to say there's going to be some constant here. This is some weird constant that I have no clue what it is. Okay, I'll just put a question mark here. We don't know what it is. Times time. That's our guess. If I were to plot this, I know I have something like this, where this right here is my amplitude. Okay, how would I find omega? I could take, if this is truly a solution to the differential equation, what can I do? I can take this, and I can put it back into here, if it's truly a solution. So substitute sub x into the differential equation. Okay, so let's do this. So I'll be nice and I'll do the, we need some derivatives here. So what's the first derivative of x with respect to t?
Negative a omega sine.
And this is minus omega a sine omega t. Okay, what's the stupid, well, this is not a proof, but I think I told you before, but I'll reiterate it. What's the dumb way to remember the minus signs that come in with derivatives with trig functions? That's too hard. That's actually thinking. I want the brain dead way to do it. So if you're taking the derivative of a trig function, you get these weird minus signs. There's a dumb way to remember the minus signs. Anything that has the word co in front of it, whether it's cosine, cotangent, cosecant, get the minus sign. There, that's the dumb way to remember it. That doesn't work with the hyperbolic functions. If you have a hyperbolic cotangent, the minus signs don't work. It only works with regular trigs. So if you're taking the derivative of anything with a co in it, if it's a regular trig function, you need a minus sign. Okay, that's the stupid way to remember it. Circle. You have to be smart for that. We've been doing it the brain dead way. Okay, we did a second derivative with this. Okay, so let's take a second derivative. So what's the second derivative?
Negative omega mega squared A cosine of omega t.
Yeah, cosine omega t. And does this have a name? That's our buddy x. So this is really minus omega squared of x. So let's substitute this all in here. So I have this equation here. This is x. This is m. This guy here we now know is this minus omega squared x. Okay, the x's go out, the minus signs go out. This tells me that omega squared equals k over m. Where omega for a string is the square root of k over m. Okay. I'm gonna do one other thing with this as well. So this right here, this is going to be the net. This is where this is going to occur in optics. Is we're going to have a really stupid model for an atom, a stupid model that works ridiculously well. Let me just, this is an aside. So in optics, what we're going to do, we're going to say here's the nucleus, it has a positive charge. Here's an electron, it has a negative charge, and we're going to send in an electromagnetic wave. This is my electric field. What is that electric field going to do to that electron? If it's oscillating? It's going to put a force on it, you know, the QE. It's going to make that electron oscillate up and down like this. Now, how do you think I'll connect in the nucleus to the electron? I'm going to say there's a spring. Okay, we're going to say that there's a spring here like this. It's completely stupid and it works ridiculously well. It's embarrassingly well how well it works. And so there's going to be a natural frequency of oscillation for this electron here, and it's going to be given by this here. What's going to happen next semester is that the frequency of this wave will either match this frequency or it won't match this frequency. Turns out if the frequency of the wave matches the natural frequency here, you're going to have these really, really big oscillations like this. That's called resonance. And what that's going to mean, that's going to strongly affect the index of refraction of the glass. And so we're going to be able to calculate how the index of refraction of this glass actually changes depending on the incident wavelength of your light. We're going to come up with a really beautiful expression for that. Okay. Which turns out to be quite important. Okay, so that's an aside. That's just something to think about for next semester. Okay, let's do one more thing with this. Go back to this graph here. Here. Okay. I think we've had this word before. What do we call that time there? Yeah, that's the time for one complete oscillation. That's the period T. This is the time for one complete oscillation. We call that T. So if I put this into the expression here, so I have x at T equals capital T equals this amplitude cosine omega capital T. At this spot right here, right, so this is T equals capital T. Okay. What does that omega T have to equal? So I'm right here. What's that omega T have to be? I mean that this is a cosine curve.
2 pi.
That has to be 2 pi, right? This would be 0. This is pi over 2. This is pi. 3 pi over 2. This is 2 pi. This omega T then has to be 2 pi. So your period is 2 pi over omega. But our omega is this. This is 2 pi square root of m over k. Just out of curiosity, what's odd about that expression? What does it not depend upon? Oh, it does. Here's the k. But what? If you tell me what the external factor is, I'll agree with you. If I give you a spring and a mass, and you will be the external factor, what will you determine for the external factor? More? Right, if I give you a spring with mass, you're gonna pull it out some distance and let it go. So the external factor that you'd be putting on it is basically how far you're pulling that spring. Okay, is there any amplitude in this expression? There is none. This does not depend on the amplitude. And this is characteristic for something called simple harmonic motion, that it doesn't depend on the amplitude. Let me explain why. We're going to do a race. So I'm going to take all of you here, all 5 of you, and I'm going to line you up. So let's say, where you all are. You're all going to be, okay, you're all going to be replaced by markers, where you all are. This is all 5 of you. You're all here. And I'm going to say, Matt, I'm going to have basically the starter's pistol. But it's going to be a weird race. I pull the trigger and all of you start running this way, like this. Okay, now some of you are going to be faster, some of you are going to be slower. So the fast people are up here, the slower people are back here. But then at some point, at random point, I'm going to pull the trigger again, and when you hear the shot go off, everyone stops and comes back. So you come back, you people come back. The question is then who wins? It's a tie. Okay, there is no winner. We're all winners. Okay, so it would be a tie. Why would it be a tie? The slow people do. Fast people like this. Yeah, the fast people, they're fast, but what do? They now have a really, really long distance to travel to get back here. The slow people be here. Okay, they're slow, but they don't have as far to go. And those two effects cancel each other. And that's why your curvature is actually independent of the amplitude. Okay, kind of neat. But now we can do something here. Is that we know that correspondence between basically between our circuit and the spring, and so now let's set that back up again. So now that we have the solution here, we're just going to go and map it onto what we had. Oh, there's the mapping on reminding me of something. So when you this is completely on the side. It's just because I'm having no sleep and my brain is just all over the place these days. You know how you have the Leibniz notation for calculus, then you also have notation like this. And so at some point when Leibniz came up with this notation, everyone realized how useful it was. And there was one of the Bernoulli brothers. There's like 8,000 Bernoulli brothers. Every single one of them is either an amazing mathematician, amazing physicist, or an amazing engineer. And I can't keep which Bernoulli it is. But one of the Bernoulli said, oh, well, the only way to solve the following problem. Well, the following problem is you have a point here, and you have a point here, and you have some path here. You're going to have an object basically that's going to be under the influence of gravity going from here to here. The question is, what shape should that line have to get from this spot to this spot here? And he said, it's a famous problem. And he said the only way you can solve it, and this shows just the superiority of the notation. Let's use this notation here, that if you do it, you can actually solve it. And it's a well-known problem. He says you can't really solve it without that. And he says, look at, and here's, and he published this and said, look, I dare anyone to try to solve this. And there may have even been a prize for doing it. I think there was like an award if you could actually solve it. So that went out, is published, and no solutions came in. And then one day, a solution came in. And what they did, they took this problem here, they mapped it to an optics problem, solved the optics problem, and then remapped it back to this, completely avoiding this notation here. Okay, and it came in anonymous. And Bernoulli looked at it and realized there was only one person that could possibly do this. That had to be Newton. So he has this famous saying where he says in Latin that, the line is known by its claws. Meaning if you're in the jungle, if you see the claw marks on a tree, you don't have to see the lion. You see the claw marks, there's a line nearby. Kind of fun. So the mapping part reminded me. So let's go back with our mapping. So we have the following. So we have our we don't have that. We had this, and that we had this equation. And we said that X goes to Q. We said that K goes to 1 over C. and that M is to L. So let's go through and do this now. So we know that omega is the square root of K over M. What does omega have to then go to? Right, because if I want here, let me just, so we know that this x equals this amplitude cosine omega t. And so what is this going to go to? This is going to go to our q, some amplitude cosine omega t. So the question is, what is the omega? So K is 1 over C, M is L. So this has to be the square root of 1 over LC, or just this. So this is going to be the oscillation frequency. Of the charge. Meaning that if I plot the charge on the capacitor as a function of time, you're going to get this right here. Okay. And what's happening with this physics right here? Okay. What happens? Well, you have the positive charge here, negative charge here. What's the charge you're going to do when the switch is closed? It's going to flow like this here, like that. But what's happening to the flux through here? It's changing. It's going to try to oppose it. So then it's going to make it go back like this. And then what's going to happen? It's going to oppose it, bring it back like this. And it's just back and forth from lenses all, which is doing this. Pretty slick. Now, this little circuit here is the basis for AM radio, the detection on it. So the circuit here. This right here is the, this is a signal detector, or let's say the tuner. This is the tuner for AM radio. And so what does AM and AM radio stand for? Amplitude modulation. Okay, so what do you have here? What that means here is the following. So the signal is going to be, this is going to be some signal from the radio station. This is some omega. This is signal from the radio station. What do you think it means to have AM modulation on it? You're going to vary the amplitude here. So what you're going to do, you're going to have some where this is really, really big amplitude. And then maybe then it goes to like a small amplitude, then a big amplitude like this. But the omega is going to stay the same. And so your information is encoded in the amplitude. That's how you actually encode the information. So what's going to happen here? Well, we have different radio stations. So we have a radio station like this. We have another radio station that's going to send a signal like this with a different frequency. Another one that's going to send a frequency like this. We're going to have a lot of different frequencies. So what happens? We have our little circuit. Here's the antenna. Okay. All these electromagnetic waves hit this little antenna here and cause the electrons to oscillate up and down with some frequency here. When you tune your, if you're listening to AM and you tune your station, what you're really doing is that we have this. What does anything with a line through it mean? It's a variable. So when you're tuning the circuit like this, what you're really doing is there's a capacitor in there. And that capacitor, basically, you're moving the plates like this. You're moving the plates so they're closer together, or so that they're not as, so they're more overlap or less overlap. And that changes your effective C. So what you're doing when you want to get a station here and you change this here, you're basically adjusting the omega of this circuit here. This omega equals 1 over the square root of LC. You're adjusting the frequency of this circuit here to basically match the frequency of the signal. And what happens is when it matches that, then you get this really, really large oscillation of the current here. That's a really, really large oscillation. That signal then gets amplified with an amplifier. And then that's sent to your speaker. That's how it works. FM is a more complicated circuit. What does FM then stand for? Frequency modulation. So what does that mean? You're gonna have a main frequency that the signal, the station is gonna broadcast at. But what are you gonna do? You're gonna encode in the information, some parts where basically you're gonna have a variation on that frequency. So instead of having this, instead of having something just like this, you have something like. You're gonna basically adjust what the frequency is coming out of the thing. And then you have to then, the original frequency of your carrier frequency, you have to figure out how to strip that off and do some other things. So it's a more complicated circuit. Okay. Questions? Okay, I want to talk then about what an AC meter measures. So I want to talk about measuring voltage, current, in an AC circuit with a multimeter. So what you do is that when we've seen those multimeters, there's an AC setting on it, and you can use it to measure basically current and voltage, and you get a number. The question is, what does that number on that meter measure? What I'm asking here, what this is asking is, what does the number on the multimeter refer to when measuring? An AC circuit. Anyone know? It's not one bit obvious. Let's try to figure out what's going on here. So let's get the voltage versus time. And it's something like that. Now, initially, before they had digital electronics, what would you do? You'd have something with a needle going back and forth. Okay, now what's the problem if I were to hook up something with a needle with this? What's the problem there? That needle is going to go back and forth like this. And if this frequency is really, really high, okay, what's that needle going to do? Like this, you're not going to be able to read it. If this is a high enough frequency, that needle's not even going to be able to respond. It's just going to be kind of just stationary almost because it can't do much. The question is, then what do you do? Okay, this is what you do. These meters here, multimeters, on AC settings, measure the RMS value of either voltage or the current. And RMS means the following. RMS means, what it stands for. Okay. Anyone know what RMS stands for? Stands for root, mean, square. Okay. And what this is really going to mean here, to really understand it, is read it backwards. Read it as square mean root. So square the mean root. Okay. That's how we're going to calculate it. So this is what we're going to do. This V here, I can write it some V naught. I'll just write it as capital V. I'll write it V naught. Sine omega t. So what do you think it means to square that? Exactly what it means. It means it's square. Okay. So this part here means to do V squared. So this is gonna be V max squared. Sine squared omega t. Okay, what does mean mean? Take the average. Okay, this is gonna be average value. And the symbol for average value is often a bracket. So that's gonna mean this. I'll talk about what to do with this. Okay. What do you think the root means? Square root. Okay, so this part here is gonna mean the square root of this here, and this right here is in your VRMS value. Okay. This value here, this is the number on this is the number actually on your multimeter. That's what that actually is. So let's do a little review of what the average value is, and then I want to work this out. I'm going to show you a trick. Trick that my advisor taught me, and I never forgot it. Yeah, I came with a little bit of an edge because he was upset that he didn't know something. But I never forgot the trick he taught me. Okay, so review. Average value. Here's F, and here's X. Let's have a function like that. This is A, and this is B. Okay, what is the area under this curve here? It's just, well, the interval. Okay, so this area here, the area under the curve, is just this integral from A to B of f of x dx. Okay. Now, how do we define then the average value? We do the following. You're gonna have some average value here. I call this not average. I'll use this notation or this notation, it's the same thing. And it's gonna be this value here. Okay. Well, how do we define it? I can look at this rectangle here. And I can ask how much area is in the rectangle. How much area is in the rectangle? Yeah, it's going to be your average value here. Times the width, which is B minus A. So we define the average value to be what? We want this area and this area to be the same. So we're going to equate this to the center average times B minus A. That's how we define average value. So your average value for something is this 1 over B minus A. Integral A to B of f of x. So let's actually not do that for this case. So let's ask. Okay, I don't want to rush it. Why don't we just call it quits for today? We'll call it quits. Then it's not a hard argument, but I want you to retain it. Okay, have a good day.